Oh, welcome back, everyone. We shall now proceed to the first technical session on Track B, which will cover the domain of artificial intelligence and machine learning. This session will be chaired by Professor Sanjoy Saha. Professor Sanjoy Saha received his BE and ME degrees in Electronics and Telecommunication Engineering from Jadavpur University in 1990 and 1992, respectively. He obtained his PhD degree from Bengal Engineering and Science University, now IIEST Shivpur, in 2006. He is currently working as professor in Computer Science and Engineering Department of Jadavpur University. Previously, he worked with TCS Innovation Lab, Kolkata, during 2018 to 2021 as research advisor for the Signal Processing Group. His research interests lie in the domain of image, video, and audio processing, physiological sensor signal processing, and data analytics. Throughout his distinguished academic career, he has published around 150 technical papers in various referee journals and conferences, and he holds a couple of US patents. He is also a member of IEEE Computer Society and IAPR. Dear Professor Saha, it is an honor to have you with us here today. May I now request you to kindly take over the session. In this Track B session, let me point out, we have 5 papers to be presented with paper IDs 6, 10, 17, 37, and 57. 3 of these papers, paper IDs 6, 10, and 17, will be presented in online mode. I would also like to remind all the presenters that each paper is allocated 12 minutes for presentation, followed by 3 minutes for Q&A. You are requested to follow the guidance of the timekeepers and adhere to the time limits. Dear Professor Saha, the session is now yours. Thank you.
Good morning to all. So as it has been already mentioned, we are having 5 papers, of which 3 are supposed to be presented in online mode. So we'll try to cover the online presentation first. So I'll request all the presenters who will be online to join in the system. So already we are having the presenter of paper number 10. So I'll request Swarup D to present his paper. The title is Deep Neural Networks in Cow Face Recognition. Swarup D from University of Mysore.
Good morning, sir. Let me share my screen. I hope I'm audible. Yeah, good morning, everyone. And I'm Swarup D. I'm from University of Mysore. I hope I'm audible and my screen is visible. Shall I continue?
You may continue.
Thank you, sir. Yeah, good morning, everyone. I'm Swarup D. I'm from University of Mysore, presenting our work on deep neural networks in cow face recognition at this prestigious ICAA 2026 conference. This paper introduces a novel dataset and evaluates the different CNN architectures for robust livestock biometrics. So let me move to the background of it. In precision dairy farming, accurate individual cow identification is crucial for health monitoring, feeding optimization, traceability, especially in rural economies where misidentification can lead to disputes, court cases, and so on, which is huge in number actually. Traditional methods like branding are prone to error, so we have turned to computer vision-based biometrics. So building upon previous work like the COW 2021 data set, our work addresses gaps in multi-breed real-world scenarios for Indian indigenous cows. And this is the first of its kind work with respect to Indian indigenous cows, as can be seen here. We capture diverse views to ensure robustness. Let's move into the next slide. In this slide, we will try to explain the need for the problem, the objectives that are involved, and the challenges that we have faced in solving this problem. The need for this problem is as follows. Existing models, as shown in the literature survey that we had done earlier. Existing models are trained on mostly single breeds, and they are also mostly of industrial setup. There is a lack of real-world data set, especially with respect to the Indian cow breeds. Indigenous breeds are very, very underrepresented, and there is no representation of post-invariant discriminant models in the entire literature that we have done within the best of our knowledge. Based on this, we have come up with some objectives. Mainly, our objectives are threefold. First, to build a new data set for this indigenous cow recognition. Second, to design an efficient pre-processing pipeline. Third, to benchmark with the existing CNN backbones. Our key contribution include our curated data set of close to 3680 images, a comparative architectural analysis, and finally, we'll be recommending the best possible pipeline, which includes ResNet, which is having close to 97.12 close set accuracy, which I'll be showing to you in the results, and lowest EER with open set verification. We have come up with something called as close set and open set. Close set is trying to identify the cow within the group, and open set is, say someone wants to bring in their cow. We should be able to say that this was not initially intended to be in our group itself. So this sets a new benchmark for our scalable livestock biometrics. We faced a lot of challenges. First of all, collecting data set under different climatic and lighting conditions, visiting different fairs. That itself was a very huge task. Other than that, cow face recognition faces several other challenges within cow breeds. If we take a breed, cows within those breeds look remarkably similar, requiring fine-grained feature extraction methodologies. Public data sets are very, very scarce, especially for indigenous breeds, and real-world variations in lighting, poses, background complicate these matters. Moreover, most prior work focuses on closed set identification, overlooking open set verification, critical for rejecting unknown animals in scalable systems. Our work directly tackles these with a robust pipeline. In fact, our open set is the first of its kind work with respect to this cow recognition. Now let's get into the data set description. These are our master student here, who were very helpful in collecting the cow. We visited different fairs. It was more than 30 different fairs, especially in the region of Mysore and Chamarajanagar district in the state of Karnataka. So here we introduce a new bovine face recognition dataset with close to 3680 high quality images from 184 indigenous cows, as can be seen here. It was actually 188 unique cows, but 4 were of not very good quality. Hence, we have reduced it to 184 cows. Each cow represents a unique class with the data collected per subject. Means per cow, it's like 4 static images with 4 different poses, left, right, up, front, and 1 video. I'll tell you the reason behind that video as well. So, a feature extraction methodology, the quality filtering of video frames using Laplacian variants, which will be using it over those videos to extract any sort of videos. Say if we miss any, if we have very bad quality images in this work, we'll try to put those into those entire collection set. Then finally, it will boil down to around 20 cows, 20 images per cow, and we have boiled down to 70s to 30 training and validation tests. We tested different 80s to 20, 65. The best was 30, 70s to 30. And images in the training set will be around 14 images per cow, and which means that in the test it will be 6. Total is 3680, means 184 into 20. So let's move into the next part of it, where the frame extraction pre-processing comes into picture. Our pre-processing pipeline starts with a video frame extraction. Filtering has sharpness using Laplacian variants to yield focused candidates. We then apply a custom YOLO V11 detector for precise face cropping, followed by a ResNet 18 feature extraction and K-means clustering to select 20 diverse images per cow. Means we are using these methodologies to extract those extra images to put into those 4 static images, so such that it boils down to 20 per cow. Data augmentation, including geometric and photometric transform, enhances robustness without oversimplifying the real-world variability here. This ensures that the quality and diversity, reducing redundancy while preserving our key features. Let's move into the model architecture. Initially, I'll be saying how the overview of the model architecture and then our proposed model. The model architecture is a streamlined pipeline. Pre-processed images are fed into a CNN backbone for a 512-dimensional feature extraction, followed by a classification head. We evaluated ResNet 50 for its deep residual learning, Inception V3 for its known for its multi-scale feature capture via parallel convolution, and also we have evaluated the efficient net V4 for efficient scaling of depth, width, and resolution. I'll tell you the advantages of each one of these, the disadvantages, and what the final pipeline is. This setup allows direct comparison without added complexity. The ResNet 50 residuals enable stable training for a fine-grained task, because as I told you, the challenges that we had was within a breed, most cows look similar if they are of same age. Now, let's get into the feature extraction part of it. Feature extraction transforms input images into a compact 5-dimensional embedding, capturing unique cows identities. These are evaluated. We evaluated 3 architecture, as I mentioned earlier, the ResNet 50, the Inception V3, and the Efficient Net V4. ResNet 50 uses the skip connections here to train deep networks without any vanishing gradient descents. Inception V3 employs the Inception modules for efficient multi-scale processing, while Efficient Net V4 is kind of, as we know, it's being optimized for model parameters through compound scaling. So all of these culminate in a global pooling for a translation invariant features. These backbones highlight the trade-off between depth and efficiency in this animal biometrics. With respect to the classification head and the loss that is present there, the classification head maps embedding to a 184 classes. As I initially told, there are 184 classes, and each cows point to a unique class. Using a fully connected layer with dropout for regularization, we optimize via cross-entropy loss, which combine softmax probabilities with the negative log likelihood to penalize the incorrect predictions. This stable loss promotes high confidence in true classes, fostering discriminative embeddings without needing additive margins. Right? So this is the kind of classification head and the loss function that we have dealt with. Now, with respect to the feature extraction part of it, let's see the training configurations that are involved, which we have boiled down to. Sure, sir. Sure. Thanks for that. We use AdamW for a decoupled regularization and cosine unhealing. Early stopping prevents overfitting. The hyperparameters were tuned using Optuna. We have used PyTorch T4 GPU. The model selection outcomes include the ResNet 50 for a balanced accuracy, Efficient V4 for slightly higher accuracy, Inception V3 for moderate performance. And let's get into the results of it. Let's start with the YOLO V11 face detection performance. Our YOLO V11 detector is trained on diverse annotation, achieving a stable MAP at 50 of around 0.77, as shown in the curve. The confusion matrix and the balance annotation confirms its robustness to variation, providing clean facial ROIs. This precision is key to our pipeline success. Evaluation scope, as I have told you, there are 2 parts. One is the closed set and the open set. Closed set is a known individual. Open set is a known individual, as it so happens that in the villages, they bring in their cow and they take more of a valuable cow, such that the number remains the same and it's hard to identify, which is a first of its kind work with respect to cow face recognitions. Data split 70:30. Now, with respect to the closed set results, as we can see, in the closed set identification, all backbones perform exceptionally well, with Efficient V4 leading at 97.28% and a near perfect AUC. ResNet 50 follows that closely at 97.19% here, with the highest F1 score, as can be seen here. Validation trend shows smooth convergence and validating our augmentation and loss strategy. This outperforms the prior words like cattle nets 91.3%. We have achieved at least a 6% hike here. With respect to the open set results, we will be using metrics like EAR, FAR, FRR, and so on. Like for open set, simulating unknown ResNet achieves the lowest EAR 0.0550. At threshold of zero point 0.8, in fact, it yields around 93% ER. This robustness surpasses efficient next before higher ER, and our model kind of outperforms every benchmark like the PANNet by at least 9%. Close-set winners don't always generalize. So we have to take the broader view, and our evaluation reveals this. We have to consider both closed-set and open-set. So based on this, in conclusion, our framework sets a benchmark for ResNet 50's balanced performance, enabling secure livestock management. With respect to the future direction, we would like to try the multimodal setup, mobile deployment, and we can see the significance, as I had stated earlier, with 97.17 with ResNet 50 ER of 0.05. But this enables an automatic contactless cow identification, traceability, health, and owner tracking. So these are the set of contribution. We have achieved every objective that we have started with our problem with, and we want to expand our data set with more breeds, Indian breeds especially, explore different transformer and multimodal models, and deploy it into edge devices and link with digital IDs and health systems. These are the set of references that we have used, and thank you for your attention, and I'm really happy to take questions, sir.
So we can take up a couple of questions from the audience. So any query? Okay, I have a very simple query. What will be the use case? For a little bit, what will be the use case for this cow face recognition? Apart from the social issues prevailing in the country, apart from that, what is the other use case?
Yes, sir. So, some of the major India is especially known for dairy farming, sir. Like with respect to the health monitoring, the feeding optimization, the traceability, especially in rural economies, we find such cases where people try to mix their animals, or if they go for grazing, it so happens that the animals are mixed, and it's really hard for them to identify, especially if they are of same age and so on. This is resulting in lots and lots of disputes. And if we are able to identify such animals with a low cost system, that's the reason why we have used very, very bare minimum Android mobile set, and and we have taken in different lighting conditions, such that it will help them resolve these disputes, especially with the open set thing. So someone cannot come in and mix in their cow and directly say that this is part of yours and this is not part of mine. So other than that, yeah, health monitoring also comes into picture. The feeding optimization also comes into picture in the rural economies, and we want to kind of bring it into a.
Just a minute, how does it can help in health monitoring? I mean, looking into the facial expression or face of the cows, can you comment on the health issue?
Exactly.
That cow
Yes,
or
yes,
the
sir.
animal.
So,
Already you have said that they are so similar that you need to go for the micro level features to identify them. And then shall we be able to look into the health issue of the animals?
yes, that's a very nice question, sir. That's one of the future work that we are trying to plan. If we try to see any particular animal, if we are able to pinpoint towards the features towards their eye and their nose, and if there is any particular extra saliva that is coming out, or if there is any, yeah, we have actually used something called as a bounded box kind of a thing here, where we can see the entire setup, right from their horns up till their eyes, up till their ears, up till their nose, and so on. These can be used as indicators to determine if there is any change in their health and so on. It's kind of an yes or no question that we are initially trying to plan. Then we will try to pinpoint to any particular diseases. That's the idea behind this.
Thank you, Swarup. Thank you very much.
Thank you, sir. Thank you for having me and giving me this opportunity. Thank you, everyone.
Okay, now we'll move for the next paper. Paper ID 6, but the authors are from Vietnam, but they are unable to join. So we'll play the recorded presentation.
New Year, everyone. New Year to everyone. New Year to everyone. New Year to everyone. Happy New Year, everyone. New Year to everyone.
a question answer session for this one, as the presenter is neither in online or offline mode. So thank you. I think the presenter was Van Yu Bui from Vietnam. So we'll go for the next paper. I mean, that is also online. Pratik Ganguly is present, right? Okay. So we'll go for the last online presentation. Paper ID 17, scheduling control task using safety guided RL. It will be presented by Pratik Ganguly from University of North Carolina at Chapel Hill.
Thank you very much for the introduction. Hello, my name is Pratik Ganguly. I'm a PhD student working under Professor Chakravarti from the University of North Carolina at Chapel Hill. I'm going to be presenting my work on scheduling control tasks using safety-guided RL. So to give you the basics of what a cyber-physical system looks like, it is any physical system which is controlled. In such a system, we have a mathematical model of the physical system being controlled, known as a plant model. This is essentially a set of equations which describe how the system evolves over time. In such a scenario, we also have a set of sensors which sense the state of the system, here represented as X. This state is fed into a controller which computes the next control input to be actuated on the physical system. So this forms an entire closed loop controller. To give you a concrete example, this could be something like a car being controlled. So the sensor here can be the speedometer, which senses the speed of the car, and then that sensed speed is now fed into a computer, here represented by the Arduino, which in turn computes how much steering angle or how much acceleration or brakes to apply to the car. We keep on doing this loop with a fixed period known as h, and this forms our closed control loop. These days, all of these controllers have now become enabled with learning components such as machine learning models. The sensor data may need pre-processing by a deep neural network, such as if we have cameras, then the RGB camera frames might need processing to estimate the distance of the car in front. So an example of such a neural network would be DistYOLO. Alternatively, if we have a car which is equipped with a LiDAR point cloud sensor, then the output from the sensor is actually a point cloud. That needs to be processed by a DNN to do object detection. So an example of that would be point RCNN. In such learning enabled controllers, we have an additional step before the controller. So here in this closed loop system, the sensor captures the sensor data represented as X tilde over here. That is fed into the DNN, which produces an inference output. That becomes the input to the controller. So as you can see, this entire setup is now more complicated, and each call to the controller and the DNN together takes a lot more time and consumes a lot more computational resources. So the challenge here is that if we have to do frequent control updates, that is, we have to frequently go through this loop, then the load on the CPU becomes higher. So the CPU utilization goes up. And as a result of which, we can schedule fewer control tasks on the same processor, because lots of computational resources will be consumed by all these tasks running on the same processor. And as a result, we won't be able to schedule as many tasks on the same CPU. Before we move on to how we can deal with that issue, let me give you a notion of what safety looks like in such a system. So in such a system, of course, there will be minor deviations from the ideal trajectory, here represented by the black line, the nominal trajectory. So if there are any deviations such as these green lines, then it's fine. It's still okay. Let's imagine if it's a car being controlled by a computer to keep it centered in the lane. So we call this lane keep assist. If it's not exactly in the middle of the lane, but if it deviates slightly, it's still fine. But if it goes beyond a certain boundary, here represented by this blue envelope known as the safety envelope, that is bad, and we don't want that to happen. So that is represented by this red line known as the violating trajectory. So as long as we are within the safety envelope, all is good, but we do not want any trajectories which go beyond the safety pipe at any given time. So coming back to the question of how can we reduce the number of control updates, at every iteration, that is at every iteration of this loop, say t equals to h times k, where k is the iteration number, what we do is we make a decision. If the system is close to being unsafe, that is, if it is close to being outside the safety pipe, then we update the control input. That is, we call the controller and compute a new control input uk plus 1 to be applied. So as you can see here, uk plus 1 equals f of xk, and f is the control algorithm. If the system is close to being stable, that it is more or less in the center, that is, it is more or less close to the black nominal trajectory, in that case, we can skip control input being computed. So what we do is we hold the previously calculated control input, uk plus 1 equals uk, where uk is the previous control input. As a result of this, we skip a call to the controller, and as a result of that, we can just skip doing all the computations which would be required by calling the controller. Now, how can we decide when to call the controller and when not to call the controller? So here is where we have used our reinforcement learning based method. In order to balance safety and utilization, we have come up with this tunable parameter alpha. So the reward function for this RL based controller looks something like this. The inputs to the reward function are the distance, or let's call it the deviation from the nominal trajectory, and the CPU utilization. And the reward is negative of alpha times distance plus 1 minus alpha times utilization. So essentially any amount of deviation or any amount of utilization is bad, hence the negative sign in the front. And if the distance goes up, then the reward reduces. If the utilization goes up, the reward also reduces. And we balance the trade-off between these two using this tunable parameter alpha. The policy looks something like this. If the deviation is greater than a certain bound, then we force our update, that is, we hit the controller. If the distance is well within the bound, that is, it is less than equal to the bound, then we hold the previous control input. We do not call the controller. So in this case, given this reward and given this policy, we use reinforcement learning to learn the optimal bound to maximize rewards. The experimental setup in our case looks something like this. We have 3 control tasks. One is a F1/10 car steering controller. We will refer to that as F1. We have a cruise controller. We'll refer to that as CC. And we have a DC motor controller, which is referred to as DC. For each of these individually, we'll use this RL-based method to find the optimal bound at which we want to take an action. If it is within the bound, we don't call the controller. If it is almost going to go outside the bound, we call the controller. And for each of these scenarios, together, we measure the maximum deviation and the utilization. The performance of the RL-based scheduler for the F1/10 controller looks something like this. On the leftmost subfigure A, we have the plant dynamics. So as you can see here, initially the system is unstable, and then we observe these huge deviations in the trajectory. But when the systems become more or less stable, then it falls into this oscillatory behavior. This is caused by the fact that the system starts going outside the safety boundary, and as soon as it is close to the safety boundary, we hit the control input, and then it becomes again closer to the nominal trajectory. When it's close to the nominal trajectory, we don't call the controller anymore, so it starts deviating again. And when it's again close to the safety pipe, we call the controller. So we see these oscillating behavior in the system dynamics. As subfigure B, we have the deviation from that nominal trajectory. So as you can see, initially there's a spike, like almost close to 0.8, but then the deviation more or less stabilizes in lower oscillatory behavior. So it oscillates between 0.2 and 0.4. And on the rightmost subfigure, you can see the processor utilization. So again, initially the processor utilization is 1 because we have to
Take
calculate
3
the initial
minutes.
control input. Sure, thank you. But as the system becomes stable, the processor utilization stabilizes at around 0.4. So moving on to the tabulated results. Here in this table, beta represents that bound which was learned using the RL strategy. So for the F1, the stable utilization as 7.62. For the CC controller, the stable utilization is 35%, and for the DC controller is 1.12%. So as you can see here, before we had this RL-based strategy, we could only schedule one controller at a time or one control task at a time, which would run with 100% utilization. But now with this RL-based schedule of a hit or miss pattern for the controller, we can now schedule 3 different tasks on the same controller. So to summarize, the RL-based controller schedule can balance safety and utilization using that tunable parameter alpha. Multiple control tasks can now be scheduled on the same processor with such a schedule. The impact on safety can be tuned using alpha. So if we want to prioritize safety, we can increase alpha. If we want to prioritize processor utilization being reduced, we can lower alpha. The control schedule can be learned offline completely. So this RL-based schedule can be learned offline, and then when we deploy this learned schedule, the new control task can be added online. So for adding a new control task to the entire system, we don't need to learn a new schedule on the go. We can just use the same schedule that we have learned offline. And that's all. Thank you. I'll now be taking questions.
Any query? Yes.
Hello, can you hear me?
Yeah, I can hear you. Thank you.
I have basically two questions. I was seeing that you are mainly focusing on the deviation to change the frequency of the control loop. I was thinking that even the speed of the car you should have taken to change the frequency of the control loop. This is one point. And second point is, in the graph you are showing, even when the deviation is almost stabilized, your processor utilization is going down. I don't understand. You understand, no? This after the 400 to 800 iteration, it seems that the processor utilization is still going down, whereas your deviation has almost stabilized.
Right. To answer
Only
your
these two questions.
Yeah, thank you. Thank you for the question. To answer your second question, it's like maybe not that apparent in this graph, but between 600 to 800, it doesn't really go down, like the utilization is stabilized. Like from 400 to 600, it falls slightly, but then from 600 to 800, there are these minor bumps and then they fall, but then the overall average utilization has stabilized to a value. It doesn't fall any further. And to comment on your first question, if you take into like, I didn't quite understand what you meant by the speed of the car, but the way I interpret it is that you mean to say that if there's a certain velocity with which the car is proceeding, then we should also use that as a parameter for taking the decision as to whether we want to make new control inputs or we want to hold the previous control input. Is that it?
Yeah, I also have a, similar kind of query. If I understand the query already raised.
Mm-hmm. So what exactly is your question?
Pratik, yeah. So if I think that if the car is moving at higher speed, there is a possibility that your trajectory. So basically, at that point of time, maybe more frequent. More frequent update may be required if the car is moving at higher speed, so that the trajectory deviation becomes less. So possibly it is related that way. On the other hand, your computation and safety, they are just, I mean, if I want to gain on one side, I'll be compromising on the other side. So car is moving at higher speed. I want to maintain the trajectory deviation within a limit. So I need more frequent update. So these issues, do you feel these will lead to a complex kind of scenario?
I understand your question. So here, two things that I want to point out are, number one, the frequency at which the control loop operates is much higher than the frequency at which the speed of the car might change. And any change in the control system is like any change in the speed of the car, let's say here in this case, is known to the controller in the sense that the controller itself was the one who calculated and applied that greater speed. And as such, if there's a possibility that at this higher speed the car might go out of the safety boundary much more easily, it is also known to the controller in the sense that when the controller senses the state of the system, it can sense that it is about to go outside the safety boundary. And at that point, again, the RL-based schedule will tell us what is the boundary at which we should start taking an action. And if it's close to that actionable boundary, then it will take new control inputs. Of course, it is understood that if we have a really dynamic system which operates at such high speeds or at such high frequencies, the safety boundary for taking an action will be much more tight. That is, we will try to keep the number of deviations very close to the nominal trajectory. That is, the bound learned by the RL-based controller will be such that as soon as it goes even a tiny bit outside of the nominal trajectory, it will start taking new control inputs. So this entire system is dynamic, of course, and it really depends on the exact physics of the system that you're trying to control. So if that system is something which is slow to react, then the boundary cannot be that tight. The boundary will be more relaxed, and you can end up with a much more greater saving in terms of CPU utilization. However, if this system is one which requires such high frequency control system updates, then of course the drop in CPU utilization cannot be much. The bounds have to be more tight and safety has to be prioritized. Does that answer your question?
Okay. I think it's gives some idea. So thank you, Pratik. Thank you very much. Now we'll move for the next paper. Again, mode switching. So from online mode, we are coming to the much more conventional physical mode. So the next paper will be paper ID 37, titled as Composite Quality Function Modeling of Instruction Response Dynamics in Sustainable Fashion. It will be presented by, I think, Shomujit Pal of St. Xavier's College, Kolkata.
Thank you, sir.
Good morning, everyone. I am Orkojit Banerjee, a second year MSc Statistics student from the Department of Statistics, University of Kolkata. And this work has been co-authored by Professor Shomujit Pal, who is the assistant of the Department of Computer Science, St. Xavier's College, and Nirvan Ghosh, a JRF at ISA Kolkata. So we have tried to link how fashion can be sort of, sustainable fashion can be quantified. This is sort of a work that we have not seen anywhere in sort of a very high dimension. And secondly, this is in a very nascent stage, but still, this is what it is. So the title of this of the talk is structured as Composite Quality Function Modeling of Instruction Response Dynamics in Sustainable Finance. The motivation was to see how sustainability and fashion link together, and this was basically done through a question answer sort of the responses were taken, and the producers or the manufacturers, they answered it according to their the queries of the customers. So this was sort of a text document, and that we analyzed. By the instruction response formats like FAQs, chatbots, style guides, etc. And the existing research actually focuses on life cycle analysis and consumer behavior, but not on the linguistic or thematic quality of sustainability advice. So the responses, I mean, understanding the tone depth and inclusivity of responses is crucial for this consumer education and the policy and the strategizing. So the responses were given by the manufacturers. That was the response given to the questions that the consumers actually asked. So that we have analyzed. The study objective was to analyze whether there is the sentiment alignment between the customer instructions, the customer questions, and the expert responses. How to quantify sustainability depth. Actually, these are the things from where we have tried to give some quantification approach. We have tried to assess inclusivity and accessibility coverage. So, how inclusive is that clothing in the social sphere, and the thematic strengths and the gaps we have done using topic modeling by the NMF, the non-negative matrix factorization approach. And finally, we have tried to give a unified composite quality index for response evaluation. Okay, so the dataset was taken from sort of a Kaggle dataset, which had 38,236 unique instructions, instruction response pairs after deduplication was performed. Instructions were as I told, the short consumer queries. The mean of those, like 17 words was the mean number of words for those instructions, and responses were almost 72 words. And the topics spanned material cares, ethics, and capsule wardrobes, inclusivity, and styling. So the workflow was, as I said, the pre-processing was taken, the deduplication was done, and then feature engineering as to what the topics. I mean, what are the factors on which we can say that whether this this piece of clothing can be sustainable or not. And then we did this NMF modeling using the TF-IDF, and a sentiment modeling was done, a sentiment depth gap modeling was done, and finally the composite Q we proposed. These were some indicators that we took into account. So the first indicator is the type token ratio, which actually is a ratio of the number of unique words by the total number of words. That calculated the it quantified the lexical richness actually. And then the sentiment was actually measured using domain specific lexicon tailored to sustainable finance discourse. The positive terms included the sustainability promoting descriptions, such as the words such as organic and reusable in that data set, while the negative words which were flagged as unsustainable practices were sort of wasteful, toxic, these words. And then the sentiment was defined by the formula, and where the sort of we have tried to give this sigma equals to 1 for the positive terms and -1 for the negative terms, 0 otherwise. And this was the mod t is the token count. And we have also tried to give a sentiment shift as to the total sentiment that is there in that sentence. So the S response minus S instructions. These were some of the factors which we included in the sustainability depth and inclusivity factor, where 0 means absolutely bad and 5 means sort of good. I mean, these were the the keywords that was used, and regarding that, the lexicon based approach was taken. This is the topic modeling where the responses were vectorized using the TF-IDF thing to capture the term importance, which is actually calculated as the non-negative matrix factorization, sort of approximates to the cross product of two matrices, W being the document topic weight matrix and H is the topic term matrix. The number of topics which was fixed is k equals to 10, which was based on interpretability and stability. And topics were labeled by inspecting high loading terms. So the examples of such topics were materials and fabric. This was one topic. Care and longevity was another. So sort of these. And then we sort of gave equal weightage to all the indicators. So sort of 1/3, and the this thing actually integrates the tone, substance, and inclusivity, enabling the direct comparison across topics, which was designed as a diagnostic rather than purely predictive metric. And sort of this is the descriptive statistics, which actually says that the descriptive statistics based on the instruction and response word counts. So the count, the mean, SD, and all the quartiles are there. Uh, this is the distribution of sentiment scores of the instruction and the responses. So the left side is the instruction, the right side is the this response. So you see that the response is sort of consistive positive shift. The response is sort of positive. And this is the average sustainability depth by topic, which actually shows that materials and fabrics are the most sustainably rich, and the actual accessories are the least. Then we have the sentiment analysis, which actually says that the mean sentiment of instructions was 0.22, responses was 0.46. So sort of positivity is there in the responses, you can see. The strongest shifts, as I said, the sentiment shift was S response minus S instruction. So that was observed in topics of care and longevity and capsule wardrobe. Which actually says that persuasive and reassuring advisory tone is required while answering the customer queries. And when we are talking about the sustainability depths, it actually says that the highest depth was taken by these materials. Sorry, these topics, and the lowest depths by these topics. The scores are there for the highest one. Lowest ones are around 1.5 out of 5. This is the result of the inclusivity dimension coverage, which actually says that the percentages actually indicate the proportion of responses containing at least one term associated with each category. How inclusive the clothing was with respect to. And these were the top keywords which were recovered from the NMF modeling. You can see from the topics of material and fabrics, the top keywords were organic cotton, recycled polyester, etc., and all the keywords you can see like that. This is the theme frequency as to which theme is taking how much counts. This is the average composite quality score. This is the final table that we have actually shown. The average Q is that value, that the metric that we have finally proposed, taking that 1/3 weights for the sentiment, depth, and inclusivity for all the topics. You can see that this capsule and timeless wardrobe topic is getting the highest average Q. This is the sentiment depth gap model, which actually you can see that the left side is the left axis is the depth, and the right axis is the sentiment. So the topics of maybe 2 and 4 are sort of very strong and positive, and and then the left side of the 8, like the general sustainability advice, you just give an advice, so that's not very much rated good by the consumer. So more so just you give an advice and you leave it, so that is not very good, but you focus more on the materials and the tailoring approach, so those are there in the top right corner, so that is good actually. So that is also being shown here, that high depth and high sentiment is being captured in those. These are the feature importance from the what are the important features actually. This actually shows that what are the important features, and then we actually used a random forest for predicting the composite quality approach rather than doing it by some linear models, because non-linearity always exists in these type of data sets. So the predictive models were OLS and random forest. OLS was roughly OLS was roughly R square was sort of 0.42 if I'm not wrong. MAE was very high. Random forest sort of is better. R square was 0.57. So the most important predictors which were used by the random forest was the sustainability depth, response sentiment, topic identity, and lexical richness. And for the brands, it actually says that embedding sustainability into styling and accessories advice is good, and we need to balance positivity with actionable depth. And for educators, it can be that leveraging care and circularity themes for behavior change. And for policy dimensions, we can say that we can target high interest but low depth domains. So the conclusion was that in this work, we introduced a composite framework for evaluating sustainability advice, demonstrated systemic tone shifts and thematic imbalances. We identified the inclusivity gaps in current discourse. And finally, the framework can be extended to other domains. Maybe we'll be figuring out on what other domains can it be, like what other data sets can this framework be enabled. And also we would be liking to use some more high-end models rather than just the basic random forest model. So maybe the new models of today, the deep learning and transformer based models, would be like to introduce in our study further. So that was all from my end. Thank you. Any questions?
So query. Node is interested in fashion. And again, not leading to LLM also. So you are not working with LLM here.
Not fully now.
So if I convert the problem in general, say query response kind of system. So there are lots of question answering or query response, this kind of system. So have you tried out any those
No,
kind
sir.
of
This is in a very nascent stage. We'll be going for some deep modelings.
Okay, then thank you, Orkojit.
Thank you.
So we'll go for the last paper of the session, paper ID 57, titled as An Adaptive System for Detecting Anomalies in Smart Electric Grids Using Gaussian Mixture Models. So authors are all from Narola Institute of Technology. It will be presented by Chandrima Sarkar.
Good morning. Good morning, everyone. My name is Chonjima Sarkar. I'm from Naula Institute of Technology, and my specialization is information technology. And I will be presenting today our paper titled An Adaptive System for Detecting Anomalies in Smart Electric Grids Using Gaussian Mixture Models. So here are the contents I will be discussing in the presentation. So at first, the question may arise that what is a smart grid? So a smart grid is an advanced electricity network, and it uses real-time sensors, communication, and control system that monitors and manages data generation, data description, and data usage efficiently. Now, in smart grid, it is very important to detect the anomalies because smart grid collect a lot more data using smart meters, and it is very natural to have abnormal activities or anomalies in those data because of many reasons like system fault or power theft or equipment failure and many more. So handling those anomalies manually is not possible because it is difficult and time consuming. That's why we need a system that will check the data set and collect the anomalies, and it will show the user the anomalies. That's why we have used a Gaussian mixture model or GMM here, because electricity consumption dataset is multimodal, meaning electricity consumption will have multiple patterns according to multiple time slot, like weekends, weekdays, morning, evening, etc., etc. And GMM handle those multiple patterns very accurately and efficiently. That's why we are using this as our model. The next slide is literature survey, where we have studied multiple anomaly detection technique, and we have also studied the limitation, and that's why we approach the GMM model, because this GMM model connects a good communication between accuracy and efficiency. That's why we have chose GMM. And after that, here is the process flow diagram, where all the methods are here, and I will be discussing step by step all the methods after. So the methods are data loading and pre-processing, then feature engineering, feature scaling, choosing the model, selecting number of components, training the final GMM model, anomaly detection, visualization, and then system update. So the first step of this time series analysis is data pre-processing, actually data loading and pre-processing. So at first, here we are using the AEP megawatt data set. And at first we have to load the data into the time series analysis. And then we have to convert the timestamp into date time format. And here we are removing the missing values and sorting the data set for the next process. The next process is feature engineering and feature scaling. So after data is loaded, we have to extract the main feature that we will be using in the analysis. Here we are using the hour of the day feature, the hourly feature. So the total feature we have here is AEP dataset feature, which is in megawatt, and the hour. And those two features represent is how much electricity is consumed and in what time the electricity are being consumed. And after the features are extracted, now we need to scale those features, because as we know, the electricity consumption data set are in large amount, like in thousands, but the hourly data set is from only 0 to 23. So if we don't scale those feature, the large feature here is the energy consumption feature will dominate the small feature, which is our feature, and the model will get biased. That's why we are scaling those feature using z-score normalization. So after scaling the feature, we have to select the best GMM model for the time series analysis, and we will train the model. So now to select the best GMM model, we need to know how much patterns we are using in this analysis. So to calculate those patterns, we have to calculate the AIC and BIC scores. So at first, we will be training different type of GMM models with different number of components or patterns. And we will be calculating the AIC and BIC score of those model. AIC stands for Icaa Information Criterion, and BIC stands for Bayesian Information Criterion. And those score, AIC and BIC score, represent the model complexity and model accuracy. Here, after calculating those score, we are prioritizing the BIC score most, because BIC score is more stricter than AIC, and It prevent overfitting the data points into the model. Also, this is useful for real world data set. That's why we are choosing the BIC score, and the score, the model which has the lowest BIC score will be the good fit for our analysis. Why? Because if the BIC score is low, then the model is a good fit. And if the BIC score is high, then model is not a good fit for the analysis. So after choosing the best model, we have to train the GMM model. In our case, the best GMM model contains 6 components, which is morning, afternoon, evening, night, weekdays, and seasonal consumption of electricity. Now we will train the GMM model according to the components, and the GMM we will train the GMM model to learn the patterns accordingly. After the GMM training, here the next step is anomaly level determination. So once the GMM model is trained, GMM will produce log likelihood score for every data point. Now, the likelihood values are the probability of the data points which GMM produces while observing each and every data point. Now, the likelihood values are very small that the computer cannot handle it accurately. That's why we took the logarithm of the likelihood values, which are less tiny, and we use that. High log likelihood means it is a better fit. And after that, thresholding are used. We have used the 5th percentile threshold. Threshold meaning we are using a cutoff value below which the data points will be marked as anomaly, and above which the data point will be marked as normal. So below 5th percentile, every data point will be marked as anomalies. Here is the adaptive update mechanism. Now, as we know, this is energy consumption changes over time due to many factors like industrial activity, then weather change, and many more. So we need a system that will update itself according to the data. Here are 2 patterns for adaptive learning factor. One is when abnormal events occur frequently, the learning factor will be reduced so that the system does not treat the anomaly as the normal pattern. And when the data remains stable, the learning rate will be increased for smooth adoption. This approach ensures the model remains effective in dynamic smart grid environment. And the data set we have used here is AEP, American Electric Power Hourly Electricity Data Set. And the source is PGM Machine Learning Respiratory. We have used this because this is widely used in many methods, and this is reliable and public. And this is the performance comparison chart. As you can see, our proposed GMM model
Chandrama, 1 minute.
have the highest precision recall F1 score. So we have chosen it. This is the visualization. The first one is the anomaly graph. Second one is the log likelihood graph. And the third one is daily anomaly counts. And the future scope we will be using in future is dynamic threshold adoption. Fixed instead of fixed 5% rule, we will be using a rule that the system will automatically generate its own threshold and real-time anomaly detection for live streaming the detection, and more inclusion of feature like weather, calendar, and contextual features. And these are the reference we have taken. So thank you. Any questions?
So any question? Yes.
This your GMM model. Is
Yes,
it a software model or hardware model? I hope it is software model.
software model.
Okay. Now suppose there is a sudden dip in the electrical grid. What is the latency that your model can detect that anomaly? Understand my question? Because you are telling it is a real-time detection of anomaly, right? Did I understand correctly?
Yes, sir, but it's in the future scope that we will be using real time. Right now, we have chosen the offline data.
Okay, okay, that is fine. But can you tell me some idea about how much time it can take to detect the anomaly? Because it is a software model, that's why I'm asking.
So I haven't.
Okay. Any other query? Okay, fine. Let us close the session. Thank you, Chundrima. So that's the end of the session. So I can find that next speaker is already waiting. So without further extension, let us conclude it.
Thank you, Professor Sanjay Shah, for chairing the session. I would now like to request Professor Anup Kumar Shensa to please felicitate Professor Shah. Can we have a warm round of applause, please? Once again. Thank you, sir. Okay, we now proceed to the last item on the agenda for this morning's session, the invited talk by Professor Swagatam Das of Statistical Institute. This session will be chaired by Professor Paramatma Datta. Professor Datta, born in 1966, pursued his B.Stat honors, M.Stat, M.Tech computer science degrees, all from Indian Statistical Institute, and received his PhD engineering from the Bengal Engineering and Science University, Shibpur, which is now known as the Indian Institute of Engineering, Science and Technology. He is currently a professor in the Department of Computer and System Sciences at Vishwa Bharati University, India. Professor Dattar is a fellow of the following organizations: IETE, IET UK, Royal Society in Arts UK. He is a senior member of IEEE and ACM. He is a recipient of numerous prestigious awards, such as Distinguished Scientist in Computer Science and Engineering Award in 2018, confirmed by the Venus International Foundation, Excellence in Science and Technology Award in 2018, conferred by the Indian Science Congress Association, Government of India, INSA Teacher Award in 2019, conferred by the Indian National Science Academy, Government of India, Lifetime Achievement Awards conferred by the VD Good Technology Factory and the Science Father, both in 2020, Global Faculty Award in 2020, conferred by the AKS Education Awards, International Scientist Award in 2021, confirmed by the International Research Award, England. Professor Datta has authored 10 books, edited 24 books, and has had around 300 research articles published or accepted for publication in various esteemed journals, conference proceedings, and book chapters in edited volumes of highly reputed international publishing houses, and he has also had 17 patents granted and published. Sir, we are truly honored to have you with us today. May I now please request you to kindly take over the session? Thank you, sir. This one? You can sit over there. Could we have the lights, please? Microphones, cordless microphone, and the lights, please. Good. Okay, Professor Swagatam Das for you, ladies and gentlemen. Thank you, sir.
So let me express my gratitude to provide me the opportunity to introduce a speaker like Professor Shagotam Das. It's a real privilege, okay? And as the session chair, it is my responsibility. So, as we all know, he perhaps needs no introduction as such, but it is rather a formality that we have to carry forward. Shagotam Das earned his BE in Electronics and Telecommunications Engineering, ME with a specialization in Control Engineering and PhD Engineering degrees from Jadavpur University, India in the years 2003, 2005, and 2009 respectively. He is currently a professor at the Electronics and Communication Sciences Unit of the Indian Statistical Institute, Kolkata, India. He is also serving as the professor in charge of the Computer and Communication Sciences Division of the Institute for the term 2024 to 2026. That means it is running. He previously held the position of professor and deputy director of the Institute for Advanced Intelligence, TCG Crest, Kolkata, from April 2023 to March 31st, 2024. So it's just few months back. His research interests encompass deep learning and non-convex optimization, and he has published over 400 research articles in peer-reviewed journals and international conferences. Dr. Das is the founding co-editor-in-chief of Swarm and Evolutionary Computation, an international journal by Elsevier. He has served or is currently serving as an associate editor of several prominent and very formidable journals, including the IEEE transactions on neural network, TNLS in short, neural networks and learning systems, IEEE transactions on cybernetics, IEEE transactions on evolutionary computation, pattern recognition of Elsevier, neurocomputing of Elsevier, information sciences Elsevier, IEEE transactions on systems, man and cybernetics systems, among others. He is a member of the editorial board of Information Fusion Elsevier, Progress in Artificial Intelligence Springer, Applied Subcomputing Elsevier, Engineering Applications of the Artificial Intelligence Elsevier, and so on. So Dr. Das has received over more than 35,000 Google Scholar citation as of now. It's extremely impressive, and maintaining an H index of 90 till date. He has actively participated in the program committees and organizing committees of renowned international conferences such as New IPS, AAAI, AI Stats, ACM Multimedia, BMVC, IEEE, WCCI, JECO, and more. He currently serves as an ACM Distinguished Speaker. He received the 2012 Young Engineer Award from the Indian National Academy of Engineering, INA, and the 2015 Thomson Reuters Research Excellence India Citation Award for being the highest cited researcher in engineering and computer science in India during 2010 to 2014. So with this, thank you. I again express my privilege. Professor Shagotam Das, please. Floor is yours.
Thank you, Paramathoda, for the generous introduction. I really feel a need to squeeze it in my website in just few lines, but thank you for the generousness to read it all. and very good afternoon to one and all. In today's next 40-50 minutes, I would like to, give you some basic ideas of what is being done in the realm of graph machine learning, and especially the latest designs and bottlenecks of graph neural networks towards assigning, ensuring fairness of the results that they provide. So we start with a very basic question that data, as we all know, could be immediately related to abstractification of any real world object in terms of certain numbers sitting together. And there has been, for a long time, mathematical structures for holding such numbers as scalars, vectors, matrices, tensors. Recently, for last 2 decades or so, people have realized that there is a huge, upfront of social media, social networks, and there is a huge progress in computational chemistry also, other related fields, where we see that one of the most natural structure for holding the data would be graphs, where we have vertices and edges between them with various edge weights or edge strengths. So that leads us to, I hope this is visible, that leads us to the graph structured data, because we already realized that a lot of the real world data does not live on grids. Grid is a very simple structure. When we talk about an image, the pixels essentially define a grid-like structure. And on the other hand, social network, citation network, communication network, modern multi-agentic system involving 400 plus agents, they all interact with each other in various degrees and could be very conveniently modeled as a graph. Okay, this could be directed, non-directed, dynamic, temporally consistent, sort of various types of graphs could be used for modeling such protein-protein interaction networks, a single huge biomolecule, or roadmaps, or scenes in an image, and so on. And when we talk about such graphs, the basic problem is the nodes of the graph could be connected to a variety of neighbors. The neighborhoods can change from node to node. And of course, some nodes are very distant, quite like an introvert node having only 2 friends. Other nodes could be very prolific and talking to lots of other peoples, like influencers having thousands of friends. So when we have such dynamic and varying neighborhood structure, then the traditional methods that work with CNNs and RNN architectures will usually fail, and that is the truth. So the basic principle of graph-based data is just like human beings. What is life? Life is a combination of connections. No human being is unless it's a very rare case, no human being is like an isolated individual. Nobody cares about him. Nobody asks or goes to his home if he doesn't come to college or office for 7 days and so on. So, and how we interact with these connections, how we talk with our friends, who are our friends, all these things also define our own characteristics, right? So that's where, when we talk about social networks, 150 years back, an iris flower data used to be magnificent, 4 features as a vector. But now every Facebook profile is a piece of data, right? And that piece of data contains image, text, video, whatnot, audio, as well as chat histories, exchanges, participation in different communities, which tells a great lot about the political, social, and other preferences of the person whose profile is this. right? If we see these profiles as individuals, if we do not care about with what other people they are regularly interacting, exchanging ideas, then the learning about that person will remain almost incomplete. That's where the graph structure and graph machine learning comes into picture. So for example, a citation network, this is the pictorial representation of the Cora citation network or Cora data set. It contains each of the node is a paper, and the links are which other papers are being referred by these papers, okay? So each color represents the class label of the node. So maybe these green colors represent papers on deep learning. They are doing their internal community-wise referencing, but often they are also referring to some statistical learning papers. They are referring to some computer science, core computer science related papers, and so on. So these cross citations are there. Maybe these red papers are from computational chemistry, and there is less cross citation between these two domains. So essentially, each of the node is a document, and the link is telling you whether these papers are referred in other papers or not. When you analyze this sort of a data set, you are not merely interested in classifying which node is belonging to which category. You are not merely interested in knowing whether these are deep learning papers, those are computational chemistry papers, etc. But you are more interested to know what are the other disciplines that the deep learning people are also interested in. What are the other disciplines where computer application people are referring or drawing knowledge from? Such information could be given or provided if we process this sort of data with the help of a deep neural network. So this is one example. Another example is, of course, biomolecules, huge organic molecules, where each node would be like this sort of atoms, and then we have the links as the bonding between these atoms. Different types of bonds could obviously represent different age features, whether it's a covalent bond, coordinate covalent bond, and so on. And we may want to classify that. Now the downstream task is we have huge molecular graphs, and we may want to classify whether the molecule is homophilic, heterophilic, hydrophilic, hydrophobic, how much, and when two such molecules are smashing with each other, that means chemically reacting, giving rise to a new graph, whether that reaction is exothermic or endothermic, and so on. Several such things could be done, provided we view this structure not just as IID data, not just as independent and identically distributed data, but also as a graph with these various degrees of nodes and so on. So now the question is how to apply existing deep learning architectures on this type of data. There are many such examples: social networks, molecules, functional networks, interaction networks. Of course, in computer vision, we are talking about such meshes which model any three-dimensional surface and so on. Then we have several downstream tasks on graph structured data. When we have this sort of a bank network, payment network data, we may want to see who are the fraudster users here, who are the fraud users that deceives lots of customers. So then the question is, can we provide a classification for each node, whether these nodes belong to a genuine user or a fraudulent user? Then we can have link prediction, strong link, weak link. What is the strength of the link between one node and the another node or neighbor? So that is essentially such presence of such links could be used very conveniently in recommender systems, where one central node or bottleneck node is providing recommendation to several, adjacent nodes that are connected to it. Then we could have graph classification itself, where we have this molecule and we want to classify the entire small graph into various chemically relevant classes. Then we could also have graph generation. There is a scene, I want to generate a scene, and in a specific geometrical structure, the traffic signals appear on both sides of the road. These orientation of the traffic signal, car and buildings and all these things from a particular perspective could be defined in terms of a scene graph, very common in computer vision community. And when we want to generate such a realistic scene by using diffusion model or similar AI, generative machine learning models, we may want to depend on such scene graphs. So these four are the most commonly encountered downstream tasks in graph machine learning, which is, of course, becoming the language of the next generation. And then we have these graph neural networks, which process the graph structured data by extracting features from the nodes, combining them with the adjacency matrix, which comprises the structural information about the graph. So it aggregates features from neighborhood and updates node representations. They are capable of tackling variety of number of neighbors and various neighborhood structures during feature aggregation, unlike CNNs and RNNs and so on. And we can do a lot of things by using GNNs, including node classification in large graphs, segmenting users in a social network based on their attributes, their relations, political opinion, meaning regularly people do it, whole graph classification, node link prediction, graph generation, and many others. In fact, graphs, knowledge graphs are at the back end of several LLMs nowadays also. So in addition to classification, regression problems can also be formulated on the top of graph data, and we can view graph valued regression as a very interesting paradigm. So for the sake of simplicity, for now, let us think of node classification problem. So in the node classification problem, basically, what we do is we try to map a subset of nodes in the graph headed by each node has a feature vector, and we try to map them to some predefined categories or classes. The problem is supposing the existence of a training set where some of these nodes are already labeled and some nodes then don't have the label. Our goal is to predict the labels or feature, of these unlabeled nodes by looking at their feature vectors. Now we could have done just stack all these feature vectors here. Each row contains a node feature vector. And then this is the feature matrix. Then we could have done normal classification, but that simply undermines the necessity of this graph structured data. So what we do is we take, and we know there is an adjacency matrix for each graph, which contains the structural information of the graph. So our target is basically to transform the features of the nodes into a low dimensional space where the structural information would be preserved. And why node embedding is node embedding? Embedding is a very important term. That means we already have a node vector. We want to transform it and generate smaller dimensional vectors which could highlight more important, more informative, and more discriminative features of each node. We are assuming that the classical features that were obtained by some measurement are not adequate enough to do that. So that's why every graph neural network has some mechanism of embedding the nodes. That means transforming the features of the nodes in a lower dimensional space. And then, so these are the original network, and there is some embedding space. There would be some transformation which would preserve some of the topological perspective of these nodes, but transform their feature vectors into some embedding space, which is basically a vector space. And then we can measure the similarity or dissimilarity of these entities in the measured vector space. Okay. Now, I hope many of you have heard of convolutional neural networks, which are very good on grids, actually. So they handle the grids of on images, and convolutional nets. Just one moment. What I give this analogy to my scholars is that the difference between regular convolutional neural networks and graph is what happens when gossip meets mathematics. So what does that mean? In convolutional net, every pixel is gossiping with its grid-based neighbors on the left, on the right, top, down, diagonally on both sides, and so on. And it is, so the life is very simple. But on a graph, There is no such regular neighborhood structure. Everyone has a different social circle. So as I said, some of the nodes are like introverts with only 2 friends. Some are influencers with 1,000 friends. Okay, graph convolution or graph neural network operation, essentially what it does is it simply says, listen to your neighbors in whatever neighborhood structure they are, average their opinions carefully, and then form your worldview. The only twist is that, unlike the real gossip, this combined worldview coming from the neighbors is properly normalized so that the influencers may not completely drown out the introverts. Okay, they may not overshadow the introverts. And after a few, now the problem is, so that is how the information from the neighborhood is aggregated. In a CNN, usually we use this fixed convolutional kernel which overlaps on some particular structure of the image and takes all the information from these grid neighbors, which has the same shape everywhere. The neighborhood is same in everywhere, and then update the weighted combination of the information from the grid neighbors, and the value of this H4, this particular entity, becomes at the next time step becomes something like this. On the other hand, when we talk about GCNs or graph convolutional neural networks, which basically became famous from Thomas Keefe and Max Welling's work in ICLR 2017, if you consider this undirected graph, calculate the update of the node in red. Now, update means this works on the basis of what we say as message passing. This is more like you have a neighborhood structure, I have a different neighborhood structure, but I will listen to the gossips and views and opinions from my immediate neighbors as if they are passing some messages to me. So I will listen here. And I also have my own worldview. So I will update my worldview based on the normalized aggregation of worldviews from my neighbors in my structure. And this would be done following some update rule. You don't need to be frightened by looking at this equation. This basically says you have your own view, which is W0, your own weight, which is Hi, which is normalized or scaled by your own weight W0. With that, you add some normalized inflow of opinions from your neighbors, and next time your weight vector or your feature vector will be updated like this. So this node, which is at the input of a graph neural network, after passing through the first layer, its weight or its feature vector will become like this. And obviously here the summation is taken over all such J indices for other nodes which belong to Ni. Ni is the neighborhood of this graph, this particular node in the graph. Weight sharing, and we of course want that we should not give different weights, so the weights should be shared across various neighborhoods. This is a big problem because convolutional neural nets operate with a fixed neighborhood structure. So same weights can be shared at different locations. The neighborhood structure is always a grid, but graph neural networks do not have that luxury. The neighborhood structure will change from time to time, so weight sharing is not possible. Invariance to permutations of the nodes is a very big problem, and linear complexity may not be achieved. And it may not be applicable in both transductive and inductive settings as well. So what we do is, during the message passing in GCN, the concept of layers in the neural network come in this way. First layer actually is operates this node features based on the first degree neighbors, which are just one link or one hop away. The second layer in the graph neural network again updates the features of this node based on the already computed first layer aggregation and the corresponding second degree neighbors information flowing from them. So we have the first order neighborhood and second order neighborhood in the 2 layers. So So this is how layer-wise the information is compressed from first-degree neighborhood, second-degree neighborhood, and the information is aggregated. And I usually prefer to talk in terms of the telephone game that ruins friendships. Imagine a large party where everyone, they sort of keep repeating what they heard from their neighbors. After a few rounds, what will happen? Every time you are repeating what you have just heard from 3 people, and somebody else is repeating what he has heard from 4 people, including 2 of the previous 3 people. So there are lots of overlaps. If this continues to happen, what will happen after some time is that all stories would become identical, bland, and wrong. This is a very big problem in traditional GNNs. When GNNs were introduced, they were giving very good result on small graphs and just 1 or 2 layers. This problem is called oversmoothing. Traditional GNNs behave like this sort of compulsive gossipers. Every layer is re-aggregating what is already aggregated previously. Eventually, all nodes will sound the same, and we say, I love to say it's like this, the deep wisdom will be achieved in terms of sacrificed individuality. Okay, so the basic thing is to avoid that, GNNs should not have more than 1-2 layers. Because of this smoothing operation, what is happening here, if you go on aggregating like this for second degree, third degree, fourth degree neighbors in a large graph, all the nodes will end up with similar feature vectors. This problem is called oversmoothing problem, which so far has limited graph neural networks from having more than 1-2 layers. On the other hand, less number of layers is responsible for sacrificing their accuracy in several use cases. So let's just once again recapitulate the difference. In a CNN on images, and the filter is passing through different pixels, aggregating in a similar manner, GCN, we can assume this convolutional kernel or convolutional filter like a more generalized neighborhood aggregation function, which can take different topological shapes as they pass over different nodes of the graph and form the output value for the next layer. In the next layer, these outputs are again processed based on the first and second degree neighbors. Third layer processes them based on first, second, and third degree layer neighbors, and so on. And the computational graph is like this. If this is the target node that we are processing, this is the input graph. So you see the aggregation in 2 layers is like this. First layer, A will directly be fed by B, C, and D. If we go to the second layer of the graph neural network, B is already being fed by A and C. This is a non-directed graph. C is fed by A, B, E, and F. D is fed by A. So you see, you are not only hearing to your neighbors. If you increase the number of layers, you are hearing yourself also too many times. So things are becoming sort of dull. You are hearing yourself, your neighbors repeatedly, and you smoothing all those things out by using some normalization. As a result of that, you are going to become very similar. This is the situation for different layers of the graph neural network. And basic approach is we are averaging information from neighbors and applying it to a neural network. Finally, the neural network, and this is done by something like this. We are averaging each neighbor's previous embedding by normalizing them with the degree of that particular node. That means the size of the neighborhood every time. So initial 0th layer embedding is just equal to the node feature. We start with the original node feature. Then as we pass over the layers of the graph neural network, we are averaging the information from growing degrees of our neighborhood. This was the original graph neural network. And finally, it is like this. You have some input graph. These hidden layers are doing that averaging, transforming the feature vectors of this input graph. Finally, you have some completely transformed feature vector. You can use that as a softmax function to provide the probability of each nodes belonging to some particular category, or you can aggregate the total feature vectors of all nodes and use in another softmax function to tell us about the class of the entire graph, not class of the node, but class of the entire graph. Or you can take the dot product of the two embedded nodes after all these transformations. These Zi, Zj are the node feature vectors after all this transformation. You can take their, dot product, and based on the strength of the dot product, you can predict whether there should be a link between them. If two nodes share many commonalities, then there should be a link between them. Otherwise, there should be no link between them. So we can take a sigmoid of this dot product, which gives us sort of a score to put a link between these two. If the score is very small, then we can simply forget about a link. So these are the three essential downstream tasks that we do with regular GNNs or graph neural networks. Then there comes also graph attention networks, which says, okay, what is attention mechanism? I hope all of you have heard of attention mechanism, okay? Because it's the backbone of all these LLMs and neural network structures. The essential crux of the attention mechanism is that you listen to your neighbors, but give them additional various degrees of importance. Some neighbors may be very, very important. They will play a major role in setting your life's goal. Other neighbors are just don't listen to them. They will spoil you. So this importance-based aggregation comes within the attention mechanism, which is merged with the graph neural networks in a very big way, getting us towards GAT or graph attention networks. I'll get back to it if time permits. So these are various, attention scores which are flowing from different neighboring nodes towards the central node, etc., etc. But what I want to show you is that initially, if the data is Euclidean, that means the data is IID, you have iris flower classification problem, you have iris flower data coming, each flower is having 4 features, and they can come in any order, they are IID independently distributed, they're not affecting each other. So they are in some Euclidean space as dots, and we can very simply do away with them by using autoencoder, CNN, RNN, etc. If the data is not in the Euclidean space, then usually, so Euclidean space means these deep neural architectures are built in for Euclidean space. If we have non-Euclidean data, which operate on some sort of topology, neighborhood topology, then we should use, even if we are in the Euclidean space, our basic operations are in the Euclidean space, we should use GCN, GAT, graph SAGE, graph RNN, and so on. And when we have non-Euclidean data and we want our models to also operate in non-Euclidean space, we should go for topological graph machine learning systems like hyperbolic GCN, hyperbolic GAT, and so on. So we want to move here. The world is already moving here with lots of use cases. So we really need some mechanism to, this is the message passing thing, where we assume that the neighboring nodes are passing some message into the central node, and the central node is aggregating that to transform its feature vector. And I told you about this. This is the node classification network. Okay, graph convolution we have already discussed. Now there comes this problem. GCN architecture is usually consisting of maximum 3 layers. Performance can degrade, the neighborhood explosion, number of neighbors will exponentially increase. Overmixing of the neighborhood information means the original node's own features, its own characteristics, will completely vanish off, and it will be completely dependent on the neighborhood aggregation. Node features become indistinguishable. And if you make GCN deeper, after some time, the node features become indistinguishable. That is the oversmoothing problem. And you can see the effect of oversmoothing. This is the COA data set. Number of layers is 2. After 2 layers, we have the vectors of each node, the feature vectors of each node. Then we plot them using a technique known as TSNE, T-stochastic neighborhood embedding, or TSNE. This TSNE is a data visualization tool which gives us this sort of structures after 2 layers. Still there is some clustering. I can see papers of the same genre clustered together. But if we go for 16, 32, 64, 128 layers, what has happened is the different clusters, I mean, all different nodes are becoming very close to each other. And even if we preserve their original color, we see that each of these strips, which are like clusters in the ultimate feature space, are mixture, complete khichdi of all different genres together. So the graph neural network, we will say they have completely failed to distinguish between papers of deep learning, papers of chemistry, papers of physics, and so on. This is where, okay, so I have already talked about it, visualization of oversmoothing. Now there comes this question, can graph neural networks go deeper without oversmoothing? So we propose some technique. This is a heuristic technique which is backed up by some theory. This is known as randomized path exploration, or RPE. So what RPE does is, it basically doesn't let all the nodes aggregate at one point of time. Rather, it explores and takes long journeys along the graph. So, as I said, most of the GNNs are like people who update their worldviews or opinions daily based on the yesterday's overheard conversations. RPE GNN is a more philosophical one. It listens quietly, take notes along its several journeys that it will make following the links, and it gives some good weightage to the link strengths of the graph. And finally, it updates its worldview only once, not at every layer, after seeing the full picture. So that means in this case, in RPGNN, the hidden layers are not the aggregating layers. The aggregation happens once for all at the end. The hidden layers are taking into consideration the path features, which could also be proposed as the difference of the node features at the two ends of the path. And there is some sort of dot product of that with the weights, weight matrices or weight vectors. So the path and the paths are taken randomly. Finally, they are rewired if the path feature strength based on this weight is quite high. So aggregation is performed in a non-recursive way from lower to higher order neighborhoods. As we move from lower order neighborhoods in initial layers towards higher order neighborhoods in final layers, the non-recursive neighborhood aggregation happens after it has seen the complete or the whole picture. Okay, this is one. And the number of random paths usually grows exponentially when the length of the paths are increased. For that, RPGNN comes with a dynamic feature computation, and the dynamic feature computation happens by taking the node and the link features almost equally in a dot product form in the aggregation function. So we take these two nodes, we take the link weight between them, and we add it with the next layer, next neighbor's link weight to form this MT to B from layer 1. This way, and then MT to C. This way, we form the entire path length by adding these link weights. And finally, from layer 2, we will recursively use this MTC for the 3 hop distant neighbors when we have passed over 3 hidden nodes. And you see, these path features like this MP or MTC is basically multiplying the node features also when we are aggregating the set of random paths. So the aggregation here is not blind. It is not happening based on all the neighbors. It is happening based on the randomly explored paths from one neighbor to others. This particular strategy is more like a guided random walk, which we to some extent explore theoretically also in this particular situation. So the standard GNNs, they're asking, what do my neighbors think or what do my neighbors talk? RPGNN instead, if I speak analogously, it is asking, what did I learn while taking a walk through this particular graph? Each random path that is being explored is like a guided random walk over the instead of just a crowded poll aggregation. And you don't average opinions mid of the walk. You accumulate the experience and average at the end of it. That is why the paths are explored randomly, features are accumulated edge by edge, and the model behaves like as I said, a biased random walk, giving more randomization along the path and less over smoothing issue. There you can see these are the usual data sets that we use like Quora, CiteSeer, PubMed. These are all citation networks. On the other hand, these are these last two, Amazon Photo and Amazon Computers, these are the co-purchase network. Co-author CS, co-author physics are the co-authorship networks. Who is co-authoring with whom? And who is publishing most frequently with other people. These co-author networks are nowadays heavily used in large machine learning conferences where we have 30,000, 40,000 submissions because there it is very much necessary to see if some unethical practice is going on. Who are the author-in-laws? This is a very important term nowadays, author-in-law. So we see if the same person is collaborating with many other persons and almost similar works are being submitted just to increase the count and so on. So these data sets are used and in the semi-supervised mode. Semi-supervised means some of the nodes are labeled, some of the nodes are not labeled. And RPE-GNN does hold an edge over all these usual results, at least in multiple cases. We see because it actually, all these mechanisms, JKNet, GraphSage, and DAG-GNN, they all have some mechanism to randomize the neighborhood aggregation in order to reduce oversmoothing. Instead of hearing the same thing, can I just sample some of the neighbors this time, some other neighbors that time, or can I just also randomly explore the path length between different neighbors and different neighborhoods with the link strengths so that I know, okay, I'm hearing to this person, but this person is not very close to me. Instead of, that means while aggregation, I should not miss any distant and quiet neighbor, provided several informative paths are converging to that neighbor. That sort of philosophy is captured in this particular walk, okay? And if you look at the visualization, this is GCN. As I said, after several 16, 32, 64 layers, everything is becoming complete mixed. It's a khichuri. The clusters that you are looking at, the stripes that you are looking at containing, papers from all genre in the Quora citation data set. But if you look at RPE-GNN, even after 64 layers, already we can see still identifiable clusters as dense patch of points sticking together. Another issue, for example, is the over-squashing issue in GNNs, which is quite serious an issue. Over-squashing means, think of an airport which has only one customs checkpoint. And in this customs checkpoint, there is a very efficient customs officer. She is handling all the incoming flights check. Flights are coming from Asia, America, Europe, everywhere. But this lady is also a human being. So she is aggregating all stories of these passengers into just 2 or 3 categories: on hold, passed, or completely withdrawn, arrested, kept in the airport, etc., etc. So these simple labels would not give us any hint of what are the stories of different people who are coming from different countries. Some people may be carrying lots of cigarettes and other things without knowing the inland laws for the country the person is arriving. But all those subtleties, all those internal details are completely lost because there is only one person and one counter, long queues, and huge number of input data or information is flowing in. This is exactly what happens in over-squashing. It is occurring when the information from many distant nodes are forced to pass through a few bottleneck nodes and be compressed into fixed size embeddings, okay? And in GNNs, as I said, in a particular layer, all the nodes features are updated synchronously. That is the original design. So we said, why doing so? Let us propose something that we called centrality aware asynchronous message passing for addressing the over squashing. Centrality aware, why centrality aware? I'm coming to that. But the crux of this work is, let us not update these nodes synchronously at the same time, but rather let us make a schedule. So you have some roads in the, you have a city, and the traffic load in the city is increasing. So there are some ways, the rewiring people, there is a huge community in Google DeepMind who do rewiring of graphs. Rewiring means we will expand our roads by smashing out all buildings that come into our way, and we will redesign our roads. This is one way the rewiring people do, because we have huge traffic. Then there are people who believe fully connected graphs are always very good in machine learning perspective because they culminate into less energy, less loss of information. So fully connected people are like who will build up roads and overbridges everywhere in the city, making it a complete mess. This particular work, which we called CAMP, aims at controlling the traffic by efficient scheduling. Okay, hold on this big road for 5 minutes. Meanwhile, pass traffics from the small roads. Wherever we have a high influx, we will let those nodes update quickly, other nodes wait quietly, and so on. So through this, I'll not go into the extreme details of it, but the working mechanism of CAMP is like that. So why we call it CAMP? Because it is centrality aware. And centrality aware means in a graph neural network, for example, also in an airport, compared to normal passengers, there would be some VIPs, right? And who are the VIPs? Like the crew members, pilots, diplomats. And if those people are delayed, the whole airport may get jammed. Okay, some big politician is not coming out of the airport. His supporters starts throwing stones from outside. The whole system gets crashed. This could happen. So these VIPs, like these VIPs, in a huge, large graph, the bottleneck nodes are those nodes which have a very high in degree. In degree means lots of information are flowing onto them. So CAMP basically asynchronously schedules the update of different nodes in the same layer, giving high chance or high probability for these bottleneck nodes to immediately update and nodes with less and less and less degree to wait and update later with more information preserved instead of getting overridden by the bottleneck nodes. That is basically the idea of CAMP, and there are some theoretical guarantees, but since the time is sweeping away, let's go into the... so this is another work which solves another very important problem of over squashing, giving us most of the time state-of-the-art result. And this is some inequality which justifies the feature sensitivity of CAMP, which doesn't include consecutive product of normalized adjacency matrices. Most theories based on matrix norms and so on. Now coming to my favorite area, bias. And we have, this is the last part of the talk. Bias and fairness is very, very important aspects of modern machine learning systems. But in fact, these are two opposite corners. Bias means your machine learning system is giving undue advantage to some specific demography, gender, race of people, especially when it is providing some service to the people, right? And fairness is the opposite. It means ubiquitous similar outcome to all people in the same periphery. So if the machine learning algorithm is biased, then it can give some very harmful outcomes, which is not the desired aspect of any responsible AI system. And why there is bias? Because the data sets are skewed. Most of the data sets, most of the data for training all these LLMs are coming from Europe, Asia, Canada, not Asia, basically, Europe, Canada, USA, and other advantageous countries. On the other hand, very few people from disturbed portions of the world like Syria, Palestine, Ghana, Nigeria, can afford to upload their worldviews in the internet. For them, 2 hours of electricity is a very big luxury, right? So as a result, a small fraction of the world population is controlling whatever data goes into the internet, and they are imposing their views as the view of the entire world. So bias can get into the machine learning pipeline from various aspects, and that data which is skewed, which is not balanced, is the training data for LLMs and other state-of-the-art AI products that we use. And nowadays, some idea comes in as a pure research idea, immediately a product is formed on that, and the product has to be marketized very fast, because otherwise some other company will do that. So there is a lack of time. Everyone is in a strange rush. There is a lack of public review of these entities, these machine learning systems. As a result, bias creeps in, mostly because gatekeeping is done by those who are in power. And if you remember this situation when this African boy uploaded the photo of his girlfriend on Insta, and they were automatically tagged as gorillas. Can you believe this? I mean, for all other things, they are saying perfect. But for this particular case, they created such a humiliating situation. Then there were some upcries and protests and so on. But it happened. Why it happened? Because they're not habituated to see a black person. They're not habituated to see an Indian person or an Asian person who hold a high fraction of the world population. So this sort of systems are everywhere, including graphs. I don't have time, but very quickly, if you look at the Google Translator, Hungarian to English translation, any proper civilized language should have gender-neutral pronoun. Like Bengali has gender-neutral pronoun. Tini, tar, she, you cannot. Hungarian is also like that. It has gender-neutral pronoun. So if you look at this Hungarian passage, this O double dot is a gender-neutral pronoun. When Google translates it into English, it is using stereotypical. She is beautiful, he is clever. He reads, she washes the dishes. He builds, she sews. He is researching, she is raising a child. So that bias goes from society into internet, from internet through the training into this sort of neural machine translators. And there is a lack of adequate public review, right? This is a very famous example. This is an Azura hand wash from UK, where the gross monthly income is $1,890. And Azura, Google, Amazon, Watson, everyone is saying it's liquid water, hand wash, bathroom accessory, toiletry. On the other hand, this is poor man's soap. Gorib manusher saban. So, and if you show, this is from Nepal, where the monthly income is $288. Azura says food, cheese, bread, cake, sandwich. Google says cuisine, comfort food, spam. Amazon says confectionery, sweet, burger. So you can see the amount of stupidity they have. This is not actually stupidity. There is no fault of the model. This is the fault of the data and the training process. Because they have never seen such soaps, which are very commonly used in poor people's toilet, may I say, compared to this Great Britain scenario and so on. So fair split is basically a way of mitigating bias in graph neural networks through sensitivity-based age partitioning. So what we do is, usually, if you are organizing a party where various people are coming, and if it is so happening that you will see that in your, I don't know, tonight is your conference banquet, whether this will happen or not. Scientists will only talk with scientists. Poets will only talk with poets. Politicians will be surrounded by politicians in a table and talking with each other. If this thing happens, then after a few rounds of such conversation, by the time when the soup is being served, every table thinks they hold the perfect worldview, actually. And there is already a cluster. This is known as homophily in terms of graph neural networks. Each node has neighbors whose labels are exactly same as the central node. Okay, this is the homophilic graph structure. When there is homophilic graph structure, there is a huge possibility of bias because there is some sensitive attributes which are only common to certain clusters in the homophily. This paper just appeared in the CIKM 25 conference. And if you look at this sort of data sets like recidivism data set, where the nodes represent defendants granted bail in the US state court system. Ages reflect similarities in criminal history and offense types. So it's a network of bail granting defendants, and we have to predict whether a defendant should be granted bail unlikely to commit a violent crime or denied bail high risk of violent reoffense based on the criminal history and offense types. Race treated as a sensitive attribute in this analysis because usually most of the law enforcing softwares which US government wanted to use since 2016, 17, 18, now the scenario is somewhat good. Most of them are completely racially biased towards the black people. So the problem is bias in the data can lead to unfair or skewed predictions based on race, amplifying inequalities in criminal justice decisions. This data set is a working ground for this. The challenge: graph neural networks can propagate and amplify biases in high-stake domains like criminal justice, hiring in a large human resource office. Traditional fairness methods usually struggle to balance the equity with task performance. Graph rewiring can erase important connections, just rewiring randomly so that one scientist is forced to sit between poets and politicians is not the last option. One good thing could be, yes, the scientist, half of the time, the scientist is led to speak with other scientists, but half of the time, he's also speaking with his fellow poets or politicians or people from different genre. Right? This happens when you come to a banquet party with your wife. You cannot only speak to your colleagues. You have to also entertain your wife and talk to her social circle and so on, which will make you much less biased. So this idea, this age partitioning idea, basically what it does is we categorize the ages as S homophilic and S heterophilic, creating two distinct subgraphs. Here the idea is each node, I mean, I'm not going into the exact technicality, but each node is as if maintaining a diary and keeping a track. Okay, I am talking to similar nodes for this much time before my aggregation. And what do I learn? I am talking to dissimilar nodes in this much time, and what do we learn? So bias, basically, please, this is the take-home message. When you are examining bias, what we are asking the machine learning system, we are asking, would you classify me in the same group if one of my attribute would have been something else? Would you grant me loan if I would have been a female candidate instead of a male candidate? Would you grant me bail if I would have been a black person instead of a white-skinned person? Right? These are the questions we are asking. So the node during the aggregation is looking at the reappearance of the sensitive attribute, which is provided for different data sets in the homophilic group, and what would have been its label if that sensitive attribute could be nullified in the heterophilic group. Then based on these two things that the node gather from homophilic and heterophilic intersections, it actually takes a decision during the update of its feature vector. And we got quite impressive results in fairness across different benchmarks like German credit, recidivism, credit default. This German credit is also quite sensitive attribute is gender. Credit system, whether you will get credit card approved or not. Bail decision, sensitive attribute is race. Credit default, payment default prediction, sensitive attribute is age. Usually aged applicants are denied of, and they have the higher probability of payment default and so on. So I'm almost at the end. I will stop here. Some classic real-world examples of graph neural networks are like this. We have this sort of alpha chip sort of network. A chip layout is not a simple task. Computer chips, they consist of several interconnected blocks, and you have to minimize the hardware layout design, you have to minimize the heat dissipation and other things. Graph neural networks are very good tools for designing such on-chip networks. They're very good things to design, this sort of molecular biological networks to predict certain functionality of gene groups and so on. And These are very important resources. Like you can search any of these in the internet, like the Mila Graph Reading Group, Graph Neural Network, Graph Representation Learning, and so on. This is the usual, journey in the world of graph neural networks. And from India, we have so big road networks, so big social networks in different domains. 70% of our youth are using smartphone. Everyone is connected to everyone else. So understanding and looking at sensitive communities which are spreading misinformation through WhatsApp universities is very important. Such community detection, harmful community operation, and filtering of news is spread across small communities could be done on the basis of graph neural networks, which are not exactly LLMs. This is something else other than LLMs. Everyone, by AI, everyone understands LLM. That is not the right thing. Graph neural networks have a lot of places where you can apply sound theory into it. So the four emerging issues that we are talking about in this talk touched one of which is ethical concerns. And these four emerging issues are all very, very important. In this era, our biggest bottleneck is how we can reduce carbon emission, how we can reduce the amount of computing. If we cannot do that, then there is no chance of democratizing this AI/ML research. It will be forever locked in the lock and key of OpenAI and related techno giants. So for reducing the computation, it is a high time we look back to neuroscience. Okay, we look back to glial cells, astrocytes, which cover our neurons. Current neurons are neural networks are extremely, extremely simple. So there is a high time that we try to build AI technology that decentralizes power, protects our people, and of course offer key benefits to the members of the marginalized community. AI will make huge progress in our society. Everyone is saying that. February, we have this AI Rajshua Joggo in Delhi, the AI summit in Delhi. But the biggest signature of a progressive society is that one in which the most marginalized person can live fearlessly with his head held high. AI should empower us to create such a society. With this, I will stop. And of course, there is a quiz for you. Who are these three people? Everyone recognizes the middle person, Professor Satyendranath Bosu, Acharya Satyendranath Bosu, in whose name bosons. He didn't got the Nobel Prize, but using his work, several Nobel Prizes were awarded. One of the recipient was Peter Higgs, in whose name Higgs boson. Yes, please. Professor Prashanta Chandra Mahalanobis, yes. Yes, perfect. This is Ronald Fisher, one of the pioneers of. And this picture was taken in the institute where from I am coming, the Indian Statistical Institute in, I think, 1959. This is the convocation ground of the institute, and Professor Bosch is giving the convocation lecture. Thank you very much.
So it was a fascinating experience, extremely enriching and extremely informative talk. And, there are several concerns which Professor Das has pointed out, rightly. Especially his concerns. Also, they are offering future directions as well. But maybe a few questions can be. Yes. Okay, so we have to sum up, right? So since there is paucity of time, we have to a bit constrained we are. So we cannot encourage questions as of now. So he may be contacted. All his details are given, contact details. So thank you for all your patient hearing and
thank you.
Encouraging presence. Thank you.
Can we have a big round of applause for Professor Swagatam Das and Professor Paramartha Datta? I would first like to request Professor Paramartha Datta to kindly felicitate Professor Swagatam Das. Big round of applause.
Sorry.
Okay. If you have any questions for this session, he will be happy to answer your queries during the lunch break. Big round of applause, please.
Thank you.
And now I would like to request Professor Debranjan Sharkar to kindly felicitate Professor Paramartha Datta. Warm round of applause, please. Okay. Thank you very much, Professor Dotto. If you look at on the screen, a QR code has just popped up. We would value your feedback. So it would be very helpful if you could provide your feedback. Visit that QR code. This brings us to the conclusion of session 1 of day 2 of Icaa 2026. We sincerely thank all the dignitaries, speakers, chairs, and participants for your valuable presence and contributions today. We shall now take a lunch break and reconvene